Hi everyone. So in today's short video we're going to continue on with multiple chirality center molecules. And we saw this in class the Wednesday before break with the di-substituted cyclohexane. And I also gave you one example of a 2,3-dibromobutane, sort of at the bottom of those pages. So I'd like to go through that one in a little bit more detail, and then we'll pick this up again in class on Monday. So this is 2,3-dibromobutane. Okay, and the way I had drawn it in class was like this. Or at least drawn one of them. And that's a little bit different than we would typically draw it. So here you can see 1, 2, 3, 4 carbons. Right? This one is a chirality center, and this one is a chirality center. H, bromine, methyl, and then the large part, and so forth. Okay? But normally we would look at a molecule sort of this way, right? And in that conformation, the molecule, if I turn this to do a Newman projection from a chapter ago, is actually in the anti. So you see this methyl is up and this one is down. But if I now rotate this to draw it like I did on the board, right? So this model now looks like this molecule, right? So you see the two bromines are both pointing out toward you, the two hydrogens are in back, and my methyls are sort of down below. So if I look at this one in terms of a Newman projection, again, looking down the bond between my chirality centers, you see this is now the total eclipsed. Okay, so I've rotated the molecule so it's now in the total eclipsed. What I'm now going to do is tilt the molecule 90 degrees. Okay, so we started out this way, rotated it to be totally eclipsed, and now I've turned it 90 degrees. And what you see when I look at the molecule this way, both of the bromines and both of the hydrogens on my chirality centers are out toward you, and the methyls on top and bottom are back toward me. This way to look at a molecule is something called a Fischer projection. And this is typically only used for molecules with multiple chirality centers. Okay, so I would represent this molecule in the following way, where this and this are my two carbons that are my chirality centers. You see the two bromines are both on the same side over here. The two H's are over here, and my methyls are top and bottom. Okay, so that would be this. So anything on a horizontal line, which is the bromine and hydrogen, are in front. Anything on a vertical line to the top and bottom are back behind. Okay? So this molecule, whether I draw it this way or I draw it this way, has chirality centers. But once again, notice this has that mirror down the middle of it. It would be that way there or this way here. Right? So right down the center, the two halves of the molecule are the same. They're symmetrical. So this, though it has two chirality centers, is going to be the same as its mirror image. So this, once again, is one of those meso compounds. Okay, so it has chirality centers, but it's the same as its mirror image. It is not chiral and does not have enantiomers. Okay, so that's another example of a meso compound. Here, drawn kind of the more typical way, here as the Fischer projection. Okay, now there are some other stereoisomers here as well. So what if I had drawn something like this? I'm going to leave this right-hand chirality center the same, have my bromine up and H back. But now on this one, I'm going to have my hydrogen up and my bromine back. And once again, those two are both chirality centers. Okay, so if I take that molecule, rotate it this way, okay, that's now this one. Okay, so again, it started out here. I made it totally eclipsed. So you can see the bromine is in front, H is behind, H is in front, and bromine is behind. So for this one now, that internal mirror, or that symmetrical down the center, goes away. So this one is chiral and is going to have a mirror image that's an enantiomer. Okay, so if I think about drawing the enantiomer for this one, do I have space here? Yeah, I guess I do. Well, maybe I'll draw it this way here. Maybe we'll do it this way. Again, it can be a mirror image in any direction, right? this one is going to be H up over here. And bromine there. And again, these are two chirality centers. Okay, so that's the molecule in its mirror image. So let me get that one together here for you as well. Okay. So there again is that molecule, right, and its mirror image. And if I wanted to draw the mirror image, that's actually the way I'm showing them there, right? So the one on top and one on bottom. But you could just as easily do it side to side too, they're mirror images. Now once again, if I take this and try to lay it on top, you notice the H's and the bromines don't line up, right? If I try to flip it over and lay it on top again, once again the H's and bromines don't line up. So these are mirror images but not the same. So this one is actually a pair of enantiomers. So these are, and again, if I wanted to draw the Fischer projection for those, right, I would now take this one that's eclipsed and flip it this way. Okay, so I would have this hydrogen, this bromine, this hydrogen, this bromine. Again, these are my two chirality centers, and then the methyl on top and methyl on the bottom. And if I draw the mirror image for this one again, okay, my bromine here, my H there, my H over here, and my bromine there, and then my two methyls. Again, these are the enantiomers. Again, just drawn somewhat different. Okay, so they're drawn in this sort of a fashion. Okay, they're this way. Okay, so again, this is the more typical way to draw that enantiomers. This is the Fischer projection way to draw. Okay, so we see this molecule, as with the cyclohexane one from class Wednesday before break, have 3 total stereoisomers. But it turns out there's a little formula to tell you about the total maximum number of stereoisomers based on the number of chirality centers. Okay, so it's a very simple formula. So it is 2 to the n maximum stereoisomers, where n is the number of chirality centers. So this molecule has 2 chirality centers, so 2 squared is 4. Now again, this doesn't say there must be 4. It says that is the maximum number of possible stereoisomers. And for this example, we only actually have 3. Once again, remember, this one was the meso, and the reason we only have 3 is because this one is the same as its mirror image. There are other molecules that would have 2 chirality centers that might actually have 4. Right? So you can imagine a large molecule that maybe has 6 or 7 chirality centers, that would be 2 to the 6th. So that's, you're going to be in the hundreds, sometimes even thousands of possible stereoisomers. Again, that doesn't mean they all actually exist. Okay? So we'll pick this up again in class on Monday after break. I hope you all had a nice break, and watch out for an email about a change in the schedule coming up for next week as well. We'll see you all on Monday.